So the use of certain different kinds of coordinate axes in one single problem has already been dealt with before. So if you remember the truss problem, which was placed in 2D and we had to do some transformation from local to global coordinate system, it was a matter of rotating the axes towards the global coordinate system for the different elements in the same structure. Now, another such coordinate system which is going to be very useful for us to be used in finite element formulation or particularly shape functions is the natural coordinate system. Now, the difference between a standard coordinate axis, the xy that we know of, and a natural coordinate axis is the way it is defined in terms of limits. Now, in general, whether it's a local or a global coordinate axis, if you have this as a direction x, then we know that at a certain length here you have xi and at a certain length here you have xj. The limits are from 0 to, let's say, the length of the element L. So that means xi is equal to 0, xj is equal to L. And this relates to every element across this same coordinate axis. Now, in the natural, so this is a standard axis. In the natural coordinate system, this changes. In the natural coordinates, we take the same member, but instead of taking the origin to be this point here as 0, we take the origin to be right in the middle of the element. So this becomes our origin 0. Now, if we say that the natural coordinate in this direction is given as s, then we know that s at this point is equal to 0. The limits in the natural coordinate system are always running from -1 to +1. Therefore, at this point s is equal to -1 and at the right point s is equal to +1. So this is the definition of a standard natural coordinate system. So if you have two nodes I and j, then the origin is right at the center between these two nodes, so in the middle of it, and then the two limits from the left to the right are -1 to +1. Now we can do some very simple manipulations by equation to see how we can relate the local coordinate system to the natural coordinate system. So if you look at this particular case here, we will be able to derive it very easily, which is of course that if we have the length still as L, then we know that this length here is L by 2 until s is equal to 0, and then this length here is again L by 2 for 0 to +1. So we know that the total distance is of course L by 2. And when s changes from one section to the other, we'll have to make a small manipulation of the s term so that we can move it towards the minus and move it towards the plus. So if we can write x is equal to, we know of course there is always a L by 2 which is going to be involved because we are always going to take the half of it, and this L can be any length, right? Length across that certain element. So that's L by 2 times we will have this coordinate s. So we know that when s is equal to 0, x is equal to 0. So this works out. But when L is equal to 0, when x is equal to minus or 0, then s is equal to -1. So this won't particularly work out, right? So when x is equal to L by 2, we have to make sure that the s is equal to 0 in that case. But at the same time, we will have to make sure when s is equal to -1, then x is equal to 0 also. So that means if I'm going to do a small calculation here and I say, okay, when x is equal to L by 2, then I have L by 2 times s. So this becomes 1 after dividing it. So s should be equal to 0. That means if the left side is 1, then I must subtract 1 from s to get to the final, I must add 1 to get to the right value of 1 by s is equal to 0 in that case. In the same way, when x is equal to 0, then I have to make sure that s is equal to -1. So that means I must make sure that if x is equal to 0, then I have s is equal to 1, s is equal to -1, so again this works out fine. So I need this is okay, this checks. And when x is equal to L, then I need to make sure that s is equal to +1. So if I have s is equal to L, I will get this as half, and then I have to, if I also add 1 here, then I take 2 on the other side, and I will get 1 here -1, so s becomes equal to 1, which is positive. That means this relation will check out by using L by 2 times s only when I have s to be equal to +1. So if I reorganize it, I will get 2x by L minus 1 is equal to s. This is my relation between the natural coordinate system and the standard or the local or the global coordinate system. Okay, so this is basically just the relation of natural coordinates. So natural coordinates have some rules. It always runs as limits from -1 to +1. The middle of the element is 0. So you can form a relation between the local coordinate along that direction with the global coordinate, with the natural coordinate, sorry. So how do we now make a relation such that we can define local coordinates for all the elements? Let's start again with our favorite, of course. Let's start with the truss element. Now for the truss element, we know we have two nodes I and j, we know it's an axial member, we know that it is a linear interpolation. So we just learned the technique of using Lagrange interpolation functions. So I'm going to set up the shape function by using Lagrange interpolation functions. So that means for Lagrange interpolation functions, I have to have a product of linear interpolation functions such that I exclude only the same node as it is for the shape function. So for node I. That means I can write here x minus xj divided by xi minus xj. So I only remove the xi, x minus xi on the numerator and xi minus xi in the denominator. If I substitute the length of the element as L, then I will get xj minus x by L, because this is actually minus L, so it becomes positive. When it goes to the top, of course. Nj is equal to the same way x minus xi by xj minus xi. So here the L is positive, so it remains x minus xi by L. Now if xi is equal to 0 in the local coordinate system and xj is equal to L, then we have ni is equal to 1 minus x by L and nj is equal to x by L. So these are one important relation that now we have derived by means of using Lagrange interpolation function. So you see, it was really quick. Now we also know that there is a certain relation here between the local coordinate system and the natural coordinate system. So I can easily replace x by L in terms of s over here. So I can write ni, let me make it very clear, in natural coordinates ni is equal to 1 minus, of course if I want to find out x by L, then I have to do some manipulation, so I get 1 plus s, because 1 goes to the other side, and then I have to divide it all by 2, which when I do some manipulation, I get 2 minus 1 minus s by 2, which is equal to half 1 minus s. And nj in the same way is equal to 1 plus s by 2, which is given as half 1 plus s. So now I have another new important result for the shape functions in terms of the natural coordinate system. So it's sort of a dimensional value. So I've basically put some boundaries to it in terms of -1 and +1. But the -1 and +1 basically is as a limit always corresponds to the total length of the element. That means if you have x divided by a certain length of the element, then you would get s. That's what basically it means. You would be able to get to the simple value of the local or of the natural coordinate system. So these are the shape functions in terms of natural coordinate system. Now, why are these natural coordinate systems so important to us? Because they look pretty simple. So why do we actually need to use them? The context is, it becomes very important when you have a certain element which is not uniform as you would expect it to be. Now here I have a certain element. It has all different shapes and all different sizes of the edges. So now what would be most useful is to transform it into an element of a type that you actually can easily form and formulate in terms of shape functions, etc. So what we see here is that every edge here has its own coordinate axis. Something of this sort. And each of these edges have their own length. This is L1, this is L2, and so on. So if instead of using each edge as its own length and its own direction, etc., if I transform it in such a way that I have all the edges that move from -1 to +1, this is y and this is x, then I would be able to easily represent it in a simple format just by changing the resident values of the x and y coordinates, because those will not change. So you have here x1, y1, x2, y2, those won't change, but you will just transform the limits of the length L1 from 0 to L1 instead of 0 to L1 to -1 to 1 in this direction. So this makes it extremely simple. And that brings us to our final topic for the day, which is called isoparametric elements. Now, isoparametric elements are very special element definitions because you use the same shape function to describe the geometry as well as the unknown variables. And the transformations, therefore, for both can also be made using the same shape functions. So, for example, if I want to use an element, which is described just as we did in the previous slide by making use of natural coordinate shape functions, then I would be able to write half of 1 minus s times ui plus half of 1 plus s times uj. This is an isoparametric element of a truss, which is described using the natural coordinates. S is equal to -1 plus 1, s is equal to 0 in the middle, where these are nodes I and j. If this is the approximation function used for the unknown displacements ui and uj, then the same equation or the same approximation behavior can also be used for describing the change in the geometry. So if you can imagine that if I have a certain edge, which is this one right here, let me mark it with a thicker one so you see it clearly, like this edge, then I can make sure that I want to transform it also in terms of geometry to this shape. That means I'm using the same shape functions to first describe how it will behave. Not only that, but also how it will be geometrically placed if the limits ran from -1 to +1 in a certain direction S. The isoparametric formulation becomes much more important when we move on towards two-dimensional elements, because two-dimensional elements are generally the ones which will be shaped in this way and more complicated, and it makes more sense to solve a more complicated problems using these kind of formulations, especially in the natural coordinate system. But you also notice that the shape functions for a natural coordinate system seem to be easier to remember, etc., also for a one-dimensional system. So you can use it interchangeably as long as you know what the limits are for your shape functions that you pick up, or the limits in general for the natural coordinates from -1 to plus 1.